All right, welcome back to 9.3. We are moving on from solving equations, and we're going to move on to a different kind of math than the ones we've done in the past. We are actually going to be looking at trig identities today, and we're going to do some proofs, okay? Which again, we really have not done much in the past, okay? So this is something new, okay? But we'll be looking at some identities that we are quite familiar with. So hopefully this will give us a good start to the rest of this unit, okay? So here we go. We are looking at reciprocal and quotient identities, okay? So what are identities? Well, an identity is a statement that relates trig ratio. So especially we're talking about a trig identity here. A statement that relates trig ratios and is true for all values of the variable for which the trig ratios are defined. So the equation, for example, the equation tangent theta cosine theta, this actually equals to sine theta. So this is what we call an identity, because it is true for all values of theta except when theta equals to pi over 2 plus pi n, where n is the element of integers. Now you might ask, well, where did I get this from? Well, this is when tangent theta is not defined. Okay, and when is tangent? Well, the question is, when is tangent theta not defined? Now recall, tangent theta is equal to sine theta over cosine theta, right? So we know tangent is not defined if the denominator equals to 0, which is cosine theta. And if you recall from the unit circle, cosine, recall, is the x value, and x values are equal to 0 at pi over 2 and 3 pi over 2 and 5 pi over 2 and so on and so on, okay? So it's every pi after pi over 2, and that's why this is not defined, or tangent is not defined at pi over 2 plus pi n. But in all other angles, this would be an identity, okay, because it's true, except again, those angles, because at those angles, tangent is not defined. Okay, so here are the identities we'll be looking at today. So again, reciprocal identities are simply secant, cosecant, or cosecant, secant, and cotangent. The quotient identities are tangent theta, cotangent theta. One thing you should be careful of is what are the non-permissible values here. Recall, denominator cannot equal to 0, right? So for cotangent, this one is kind of strange because you actually have both of them. This is because cotangent could be written as cosine theta over sine theta, recall. Okay, therefore sine theta cannot equal to 0. That's where you get this. Or it can be written as 1 over tangent, but recall tangent is sine over cosine. And you can see cosine right there, there is the denominator, and therefore that's why cosine theta cannot equal to 0 as well. Okay, so just be careful what the restrictions are. Okay, so let's take a look at our first example here. It says verify that cosecant x plus cotangent x is equal to 1 plus cosine x over sine x. Now, so verify simply means that we're going to check if this is true for this angle. Okay, so for this angle only. So other than this angle, we cannot say anything else. Okay, we can only say that this equation is true for this angle, and we want to verify that. Okay, so let's check. Cosecant, recall, is 1 over sine, so this is going to be 1 over sine x. We know the angle is pi over 3, so that's what we're going to write. Plus cosine is cotangent is cosine over sine, so cosine pi over 3 divided by sine pi over 3. We want to see if this is indeed equal to 1 plus cosine pi over 3 divided by sine of pi over 3. Okay, now pi over 3 is one of the special angles. So I'm going to draw my special triangles right here. Here's my pi over 3, pi over 6, 1, 2, root 3. So 1 divided by sine of pi over 3 is going to be 1 divided by root 3 over 2, plus cosine of pi over 3 is 1/2, sine of pi over 3 again is root 3 over 2, equals, sine pi over 3 is root 3 over 2, we have 1 plus cosine of pi over 3 is 1 out of 2. Now you can see clearly they would equal to each other here because we have the common denominator here. So if you add them together, you get 1 plus 1/2 divided by root 3 over 2. And that's exactly what we see on the right. So they are definitely equal to each other. Okay, so again, we verified that this is true for this angle only. Okay, that's not a proof. It's not we didn't show that they are actually equal to each other for every other angles, but we only show that it's true for pi over 3. Now, before I show you part B, I'm going to actually continue with part C first. It says state the non-permissible values, which means we're looking for the values of x that makes the expressions or this equation undefined, or any of these terms undefined, which means we got to look for the denominator, because as long as the denominator is 0, then it's undefined. So if we look at this first line right here, you can see we got a denominator in sine, so sine x cannot equal to 0. Okay, we'll solve for x later, but for now, we know that sine x cannot equal to 0 because that's what our denominator is, it's sine. And I move to the second expression, that's cosine over sine, so which means just sine. And on the right-hand side, you got 1 plus cosine over sine x, so there you go, that's our sine x cannot equal to 0. However, we do have cotangent in the second term, and recall cotangent could also be written as 1 over tangent, which means and we know that tangent is sine over cosine. So that means cosine x cannot equal to 0 as well, right? Let me write that down here. Cotangent is 1 over tangent. I think I showed you this on the top right here, right? That's this portion. So basically, cosine cannot equal to 0 as well. Okay, so I'm not going to repeat that. Okay, so therefore cosine x cannot equal to 0 as well. But now we need to solve. Okay, I think I solved for cosine x earlier. Right here, right? That's when cosine is 0 because it's for tangent. So in this case, pi over 2 plus pi n cannot equal to x. And in this case, x cannot equal to pi n. Okay, because sine, recall, is the y values, or are the y values. So y values are 0 at pi and 0 and 2 pi and 3 pi and 4 pi and so on. Okay, so these would be our non-permissible values. Okay, or sometimes I call it the restrictions. Okay, so here we go. Part B, this is something new. We are trying to prove that they are actually the same thing algebraically. Okay, so I would suggest you to use this t-table. Obviously, you don't have to, but I really encourage you to do it, because when you prove an equation, you cannot, okay, let me repeat that again. You cannot say, oh, okay, I'm going to minus cotangent x here and minus cotangent x here. You can't move things between between different sides. Okay, you can't switch them. Okay, you can't cross multiply. Okay, you have to work whatever that's on the left. You can only work what's on the left. Whatever on the right, you can only work on the right. You cannot do any, movings. We're actually not solving, right? So for solving, you can actually move things around, but when you're proving, what's on the left must be kept on the left. What's on the right must be kept on the right. That's why I like to draw this t-table, so there's a line in the middle to remind me that I can't move them, okay? So be careful. Now, there are some tricks to prove. One of the most important or basic trick to do is to change everything to cosine and sine. Especially as a beginner, I would really suggest you to change everything to sine and cosine. So here we go. Cosecant is, we know that 1 over sine. Cotangent is cosine over sine. Okay, so a couple of things to do, right? Again, first thing is always to change to sine and cosine, and the other thing is simplify the more complicated side. Okay, don't make the simpler one more complicated. That makes no sense, right? You want to simplify rather than make it more expanded form, right? Okay, now we got two fractions here. Now we just need to add them together. Well, we have the common denominator sine x, so if we just add them together, we get 1 plus cosine x. And you can see that's exactly what we have on the right, right? You actually don't need to do anything on the right, because you already show that the left-hand side, once you do some manipulation, you can actually make it the same thing as what's on the right. Okay, so then that's it. We successfully proved that indeed cosecant x plus cotangent x is equal to 1 plus cosine x divided by sine x. Okay, this is how you do it algebraically. Okay. All right. Again, here are some strategy that we can use. Start by simplifying the side that's more complex, and always write everything in terms of sine and cosine. Okay, so here is one question for you to practice, and I'll let you try it. Or actually, a couple questions for you to practice. Good luck. I will show you the full solution too. All right, so let's take a look. I think for the first one, clearly, the one we need to simplify is the one on the left. Okay, so we have sine x, and that's so the first step. Again, start by simplifying the easy side or the more complex side, and then write everything in terms of sine and cosine. So secant is the same thing as 1 over cos. And then we have cotangent, which is cosine over sine. Okay, so now what we have here is we have, next step, we can simplify this. This is sine over cosine, right? That's on the top. Sine times 1 over cos is simply sine over cosine. This is division. Remember, division is the same thing as multiplying or multiplication of its reciprocal. So this is divided by cosine over sine. So if we flip to a simple multiplication, it becomes multiplying by sine x over cosine x, which then we get sine x times sine x, which is sine squared. Cosine times cosine is cosine squared. We know that sine over cosine is tangent squared. And there you go. That's the same thing on the right-hand side. We got tangent squared x right here as well. Okay, so that's how you prove the first question here. Now, just to remind you, I think this section is not too bad, but as we get to see more complex proofs, notice that there will be more than one way, definitely more than one way to prove things. So, but for now, these are basic ones. So usually, if you just change everything to sine and cosine, you'll get to your final result. But you definitely will be looking at different ways of proving. So when you practice it, your final answer might not be the same as mine, which is okay. But just make sure that you follow the rules, right? You can't do something that's not right, and then somehow you get to the final answer, then it won't be right. Okay, you can't make things up. All right, so that's the proof. The non-permissible values. So again, we're looking for the denominator. So look at step by step. First one right here, I see that I have cosine x over here, so I know that cosine x cannot equal to 0. In the denominator, I have sine x, so that is sine x cannot equal to 0. Cosine x, that I already have. Cosine squared, I already have. So there we go. So only these two. So again, I think these two are pretty basic. That means for cosine, x can equal to pi n. For pi over 2 plus pi n. And for sine x, x cannot equal to pi n. And we know that n is simply the element of integers. Okay. Again, these are basic ones. Okay. Number 2, how about this one? Hopefully you got this one as well. This one we probably actually need to simplify both sides, but we'll see. Let's for sure. Oh, I don't know what happened to the x here, x there. Okay. For sure we need to simplify the left-hand side, I think. Okay. Okay, you know what? Let's see. I don't know the answer. I haven't done this question yet, so I don't know. Okay, so sine x plus tangent is sine over cosine out of 1 plus cosine. Okay, now in the numerator, I do see a fraction, so I need to add them together, which means I need common denominator. So I need to have cosine x, and that means this is going to be sine x, cosine x. Sine x, cosine x, plus cosine x, and we have sine x on the top. You still have the 1 plus cosine x here. Now you need to add them together, but what I see is on the numerator, both terms have sine x. So I'm going to factor out sine x as well. Okay, so if I factor out sine x, I end up with cosine x plus 1 divided by cosine x. And again, I'm dividing by 1 plus cosine. So when I'm dividing by that, that means I'm multiplying by 1 over 1 plus cosine x. And notice this is 1 plus cosine x, this is cosine x plus 1. They are exactly the same thing. So I can cancel them. So I actually end up with sine over cosine. Okay? And guess what? I'm going to change the right-hand side as well because I'm kind of running out of room here. I have sine x times secant x. We know that secant x is 1 over cosine x. oh, look at that. So sine x times cosine, 1 over cosine is simply sine x over cosine x. And there you go. I should really write one more line. So then this becomes sine x over cosine x. So they are exactly the same thing. Okay, don't leave it like this. Okay, don't leave it there, because once you cross it out, you should have a final result right there, sine x over cosine x. So there you go. They are equal to each other. Okay, now let's take a look the non-permissible values here. So again, for the denominator, I see cosine x right away. So cosine x cannot equal to 0. And then I also see this denominator right here, 1 plus cosine x. So that means 1 plus cosine x cannot equal to 0. Okay, now this one we already know. That means x cannot equal to pi over 2 plus pi n. Okay, this actually means cosine x cannot equal to -1. Now recall, cosine x equals to -1 here, right? Because cosine is the x value of this unit circle, and x is -1 right here. So in this case, x cannot equal to pi plus 2 pi n. Okay, not just pi n, because it's actually okay to be there. It's just here that's not okay. So which means it's every rotation. So it's 2 pi n. And there you go. N is the element of integers. Okay, that's it. All right, so that's the proof. Again, proof usually is quite difficult for students because it's something new. You haven't done it before. And sometimes it's just algebra, and then if you don't use the right steps, then if you don't see it, you don't see it, right? So it could be difficult, but I personally really like to prove because I think it's kind of fun. It's prove things. It's kind of fun when you get it right. It feels good. Anyways, so that's the proof. Okay, so you have a lot of practice in the book, so give that a try. Okay, example number 2, we are solving equations. Okay, so this is something we've done before. Okay, so I wouldn't say less challenging. It's just we are more familiar with these. Okay, so let's see. We got 2 sine x plus 5 is equal to 3 times cosecant x. So again, I would change everything to sine and cosine. Cosecant is 3 over sine x. Okay, and now I'm going to multiply everything by sine x. So then I get, because I got denominator here, so I get 2 sine squared x plus 5 sine x equals 3. This is a quadratic equation. I'm going to move my 3 to the left. I get 2 sine squared x plus 5 sine x minus 3 equal to 0. We can factor this because it's a quadratic equation. Okay, you should get 2 sine x plus 3 here and minus 1 here, I think. Let me just double check. That's plus 6 minus 1. Perfect. So this is how you factor this. Okay, so if you're not sure, just treat this like a squared, and this is just a. So 2a squared plus 5a minus 3. If you factor that, you should get 2a minus 1 times a plus 3. Okay, so if you treat this like 2a squared plus 5a minus 3, so I simply let a equal to sine x. This is what you would get. And then obviously at the end of the day, we're not solving for a, we're solving for x. So you gotta substitute sine x back to a, and hence you get 2 sine x minus 1 and sine x plus 3. Okay, so this means either sine x equals 1/2. This came directly from that. Okay, you move 1 to the right and divide it by 2. Or sine x equals -3. Okay, now right away I know this is not possible. Okay, if you recall, sine for both sine and cosine, without any transformation, the maximum will be 1, the minimum is -1. So there is no way for sine x to be -3. Okay, again, the minimum is -1. It cannot be anything less than -1. Again, this is without any transformation, of course. Okay, so sine x equal to -3, that's not possible. However, sine x equals to 1/2, that is definitely possible. Now, when does this happen? Again, well, this is a special triangle, if you recall. Let me call this 1, 2 root 3. So this is pi over 6, and that's pi over 3. So sine x equals 1/2. That means the reference angle is pi over 6. So x reference angle is pi over 6. We're looking at positive 1/2. Is there a domain? Yes, we're looking at a domain between 0 and 2 pi. Okay, now sine is positive. Hopefully you remember this, is between quadrant, or sorry, sine is positive in quadrant 1. Therefore, x1 is pi over 6. And the other one is in quadrant 2, so this is pi over 6. Therefore, angle 2 will be pi minus pi over 6, which is 5 pi over 6. Okay, so here are your two answers. Now, you should always check the non-permissible values, okay? Because sometimes your solutions and the non-permissible values are the same. And in that case, you'll run into, a problem. Well, it's not really a problem. You just need to reject the answer, right? So let's take a look. Well, the only part that has denominator is the cosecant, which is sine x. So we know that sine x cannot equal to 0. Now, if you look at this and look at our equation and the restriction, they don't actually interfere each other. So actually, we are fine. But if you want to just, be careful and actually solve it, sine x equals to 0 at pi n, right? And NEI, or yeah, that's right. N is the element of integers. Again, they do not interfere, so we are okay for these two solutions. Okay, so that's our part A. If you want, you can try part B yourself. Pause the video and see if you can do it, okay? All right, part B, this one is slightly tricky because there's sine x and there's cosine x, but we can't. One key to solve equations, I might have mentioned this to you in the 9.2, I can't remember if I did it or not anymore, is that you want to make sure everything is in terms of sine and cosine. One of them only, right? It's either everything in sine or everything in cosine. However, this case, we got sine and cosine. We can't change sine simply to cosine, okay? We can't do that. But what we can do is we can actually combine sine and cosine to make it tangent, okay? So I'll show you this. We can simply, let me think about this. I want to have sine over cosine. So I guess I want to move the root 5 sine x to the right. Okay, so I'm going to do that. So that's negative root 5 sine x. And now I can divide both sides by cosine x. And if I do that, I get 1 equals negative root 5 sine x over cosine x. Now recall, sine x over cosine x is simply tangent x. So now what I'm going to do is I'm going to move the negative root 5 to the left. So I get negative 1 over root 5 is equal to tangent x. And now you can see this is one simple trig equation that we can actually solve. Okay, so first of all, notice that we do have denominator here, right? Cosine x. So you have to check for the non-permissible value in a second here. So to solve for x, again, we need to find the reference angle. This is not a special triangle, so you need to use a calculator. So let's pull it out. Let's try this. Make sure in the radian mode, because the question is in radians, right? Between 0 and 2 pi. So here we go, radian mode. Okay, so 1 divided by root 5. And I always preach that when you take when you try to find the reference angle, you always take the inverse trig of the absolute value of the ratio, right? So notice it's negative 1 over root 5 here. But for my reference angle, I only put positive 1 over root 5. Okay, anyways, the reference angle to two decimal places is 0.45. Okay, 0.4472133195, whatever, 0.45. Now, recall, tangent is negative, and tangent is negative in quadrant 2 and quadrant 4. So here is 0.45, and here is 0.45. So x1 would be pi minus 0.45. x2 would be 2 pi minus 0.45. Okay, and then we simply put these values into calculator. And don't forget, don't actually use 0.45, okay? You use pi button and then minus the enter on your calculator. Okay, don't round until the very, very end. So you should get 2.69 radians. And the other one, so now in order to avoid rounding, I'm going to do inverse tangent again. 1 out of root 5. And then Hold on a second. How come I get a different answer this time? What's going on here? I got 0.42 instead of, instead of 0.045. Okay, 1 divided by root 5. Oh, I forgot to inverse tangent. Oh, shoot. Okay, that's why. Inverse tangent, delete, enter. Okay, sorry, you don't get 0.45, you should get 0.42. Here we go. Mr. H added again. Okay. Man. Okay, pi minus that. Okay. Where's my pi minus? Okay, pi minus enter. Okay, you should get 2.72 instead. Okay. Inverse tangent. 1 divided by root 5. And then we have 2 times pi minus enter. This one you should get 5.86. So these are your answers. Okay, and again, if you want to check for non-permissible value, again, that's cosine x cannot equal to 0, which again has nothing to do with our solutions here. So we're fine. Okay, these are okay. All right, that's it for this lesson. Again, there are questions for you to practice. Let me know if you need help. Okay, otherwise, good luck. See ya.